Obviously, we're all here for Karan Cambly's PhD dissertation and defense examination. So the way this will work is that we'll ask Karan to present his work and include everybody in that discussion. And if you have questions about the work or anything as we go along, feel free to interrupt. But we'll save sort of probing questions for the end. And then what we'll do is excuse the general public and have a meeting with Karan and the committee. And at that point, we'll excuse Karan, and the committee will come up with a list of our requests for Karan in order to partially fulfill requirements for graduation, right? So Karan came to us from Georgia Tech, where he got his master's degree, and his undergraduate degrees are from IIT Delhi, and he's been supported by the Electric Power Research Institute and Department of Energy for a majority of his time here, and so he's going to talk about his work over the past couple of years here. So go right ahead, Karan. Thank you.
Thank you, Dr. Bradley. Hello, everybody. I'm Kiran. I welcome you all for my PhD defense on implications of temporally and geographically realized.
Just in time.
We're on the title page.
Oh, nice title.
Okay, so I welcome you all for my PhD defense on implications of geographically and temporally realized energy use for electrified transportation. So before going into the details of the presentation itself, I would like to extend a lot of gratitude to a lot of people who have contributed at different points of time, beginning with Dr. Bradley. He's been a great inspiration for myself and a lot of other students here, and I'm sure he'll continue to be. Thank you for providing this opportunity. And I would also like to convey my gratitude to my honorable committee members, Dr. Brian Wilson, Dr. Kirkpatrick, and Dr. Peter Young for accepting to serve on my committee. Then I would also like to thank my awesome lab group members who've traveled this journey with me in all these years. So going back to my school at Georgia Tech and also IIT Delhi, there's been a great many number of professors who have influenced me to pursue research, and I would like to take this moment to thank them as well. And of course, my present and past industry colleagues, they've added a extremely good value addition to my knowledge. Finally, I have my family and friends who stood by me in all my endeavors. And I would like to dedicate this work to Anusha. Okay, so here's a brief presentation outline. First, I'll be talking about the motivation for this research. Now we'll see how the motivation leads towards a set of objectives, and these set of objectives will be further classified into main research questions. Next, I'll briefly go over some of the prominent works related to the research questions. After this, I'll discuss the methods developed in detail and also discuss the overall workflow. Moving on, I'll present key findings associated with each one of these research questions. Finally, I'll end my presentation by highlighting some major contributions towards advancing the state of art, and also open up the presentation hall for questions and discussions. Okay, so internal combustion engines have been driving the transportation sector for more than a century now. Despite that, the best conversion efficiencies are only at 18% for gasoline and 22% for diesel engines, while that for electrochemical conversion efficiencies are 3 to 4 times higher. So looking at the well-to-tank efficiency, the efficiency for electric transmission stands at 38%, which is only half of that of the conventional fuels. So combining these two efficiencies results in well-to-wheel efficiency, which it can be clearly seen that the electric vehicles now stand a chance of being twice more efficient than the conventional vehicles, purely in terms of energy conversion. Okay, so despite these inherent higher efficiencies, the electric vehicles are still not popular, and the popularity of them are still at the primitive stages. So the end user obviously understands that gasoline is bad for pollution, in terms of pollution and such, but he wouldn't compromise on the range freedom offered by these conventional vehicles. So the success of the electric vehicle technology will also ultimately be decided by the end user and his experiences. Meanwhile, the automakers are definitely in the race to manufacture these electric vehicles using advances in battery technology. Now, speaking of which, it has taken more than 154 years for the specific energy of the electrochemical species to go from 30 watt hours per kilogram to 300 watt hours per kilogram, which is the state of art used in the present day electric vehicles, while the specific energy of gasoline is still 65 times higher. So on the other hand, the policymakers are more interested in reducing the US oil imports, which will greatly enhance the nation's energy security. And since transportation sector is one of the major contributors, it is imperative upon them to support developments in to support advanced vehicle technologies. So the DOE's Freedom Car Movement and ARPA-E HEATS program are evidence of such initiatives. And of course, environmental groups, they seem to consider EV technology as more clean and less pollution, and making the neighborhood pollution free. But they're only as clean as long as the energy, energy is from the source, from a renewable source. So looking at this a little deeper, it is very easy to see that there is a clear disconnect between the way these stakeholders interact with each other. Now the reason for these disconnects is because the metrics that each one of these stakeholders use to relate to the EV technology is completely different. For example, end users are more concerned about the electric vehicle range, while the policymakers are more worried about reducing the dependence on foreign oil and increasing energy independence and increasing national security and such. While the automakers are catering to more focused towards catering to the needs of end user and also adhering to the rules and regulations of policymakers, while also appeasing environmental groups. But without the blessing of the end users and their experiences, it's very difficult for EV technology to go into the mainstream. And so it becomes very important to understand and analyze these metrics carefully towards assisting their implementation in the mainstream transportation fleet. Okay, so here again, now let's take a look at the gasoline consumption in the US itself. So this pie chart here, it represents the annual gasoline consumption divided among industrial, transportation, residential, and commercial sectors. Now the transportation sector is further divided into energy for vehicle traction and also energy for passenger comfort. So now the energy for passenger comfort, it can be seen that it is more than the gasoline consumption for commercial and transportation sectors put together. So these percentages can be further translated into the actual gasoline numbers. So according to US Department of Transportation, an average vehicle in the electric light duty light duty vehicle fleet consumes about 687 gallons of gasoline every year, of which 60 gallons of gasoline is used towards operating thermal comfort, which is basically operating air conditioning requirements. Now this 60 gallons, when it is compounded with 250 million vehicles in 2008, it results in providing energy for almost 40 million US homes at 9,000 kilowatt hours annually. Now with electric vehicles, they do not have the luxury of waste heat for winter conditions, for heating the cabin. So these numbers will again increase with the electric vehicles. And also from this market forecast plot can be seen that the demand for these electric vehicles are continuously increasing. Okay, so until now we have seen how electric vehicles can can eventually become a long-term sustainable solution for driving the transportation sector. But before coming to any conclusions, the big questions that we are seeking to answer here is how much energy does the electric vehicle fleet compare to that of a conventional passenger vehicle fleet? So this would help the policymakers to plan for the national energy requirements for transportation sector. Okay, so as pointed out before, the main energy sinks for automobile is towards traction and towards HVAC requirements. So over the last century, a lot of efforts have been gone towards improving the fuel economy by strictly implementing CAFE standards and other regulations. So the energy for traction has been well established in the due course for various driving conditions and such. But the energy expended towards HVAC requirements are not easy to quantify simply because of their stochastic usage patterns and the non-availability of relevant data for modeling purposes. So it was not until 2000 the first studies towards determining the amount of gasoline consumed towards thermal comfort requirements towards AC systems were initiated at NREL. So here's a listing of some of the prominent works performed at NREL. And so all these works were, the effort in all these works were directed towards modeling thermal comfort requirements in conventional vehicles, developing vehicle and component testing, and also developing advanced testing facilities using mannequin and setting up advanced climate control laboratories.
What is mannequin?
So mannequin is just it's an experimental test setup resembling a human with all the sensors and stuff that is expected to react in a similar way as a human. Okay, so on a parallel track, DOE's vehicle simulation software such as Advisor and Autonomy were focused more on improving the traction predictions and also developing powertrain architectures while setting HVAC loads as a non-dynamic constant. So the process of understanding the sensitivity of HVAC requirements and also evaluating the total energy consumed by an electrified light-duty fleet forms the basis for my research question 1. Okay, so in the previous slides, in the previous discussions, we noted that the EV user will connect with the electric vehicle technology more in terms of electric vehicle range. So, and he's more concerned about the EV range. So this concern will only get aggravated based on the climatic conditions under which they operate. So towards this goal, the HVAC energy computations from the research question 1 would be translated into a hypothetical driving scenario to understand the geographical and temporal sensitivity of EV range. And so the research question 2 will also be extended and used to investigate regions within US which could be most likely beneficial from EV technology. We would also use the results to simulate day-to-day electric vehicle fuel economy as against EPA and auto manufacturers' claim, and also look at evaluate benefits of cabin preconditioning. Okay, so going into research question 3 is what accessory systems or technologies can improve the environmental performance and utility of electric vehicles, and what metrics or methods can be used to evaluate economic, geographic, environmental, and energy life cycle of proposed technologies. So the idea here is that EVs have a single onboard energy storage device to support all the vehicle's functionalities. So by decoupling the energy demanded by the HVAC from the main onboard storage device, it should be possible to travel much farther. So one of the goals of ARPA-E HEATS program is to identify and support the development of such HVAC technologies that will enable this functionality. I'll be presenting sample sizing requirements for a phase change based alternative HVAC technology, and we'll also be looking at a multi-objective comparison of conventional HVAC systems, which is the state of art in the existing vehicles, alongside with the phase change technology that I'll be discussing here, and also the ARPA-E HEATS goal. Okay, so before going into the details of the model itself, I would like to highlight some of the existing thermal comfort model and the work done by the previous researchers. So one of the most widely used approach towards thermal comfort was developed by Fangers way back in 1970s. Now, Fangers model basically combines two physiological variables, which is personal metabolism rate and clothing insulation, with 4 physical variables like relative humidity, air velocity, average radiant temperature, and average air temperature, to generate an index. Now this index can be used to predict the average thermal sensation of a group of people in space. But there were also many studies that talked about the measurement errors from the prediction based on Fangers as against the measured thermal sensation values. And there have been many studies, other studies, that talked about the complexity involved in controlling all these variables simultaneously in order to generate a useful thermal sensation map. But NREL's models were developed based on Fangers' description of thermal sensation mode, also predicted mean mode. Now PMV is related to the heat balance on the body. A metric called predicted percent dissatisfied was defined, and so it's basically a function of deviation of a person's heat balance from a thermally neutral sensation. So a positive value of PPD is significant. It indicates that the person is most likely to feel too hot. So NREL used this PPD metric as a statistical representation of percentage of time the AC would be turned on. So on the limitation side, the negative deviations indicative of cold cabin conditions were not considered. Now this is important in terms of electric vehicle perspective, because AC, both energy for AC and heating needs to be considered with equal weights. And also the models do not consider time-resolved temperature fluctuations in cabin space. And most importantly, Fanger's model were developed towards thermal comfort requirements in building cooling, building applications. And I'd also highlighted before that DOE vehicle simulation softwares like Advisor and Autonomy, they do not have the capability to capture the complex functioning of complex HVAC systems. And so for EV, so for EV we need a model that is more amenable in capturing the sensitivity of cabin with respect to changing environmental conditions. And so we decided to go with a state space representation of cabin space. Okay, so here's some details on the control volume based thermal comfort model. Unlike Fanger's model, which was thermal index based. Okay, so here's my cabin control volume, and the temperature of the cabin is obviously affected by the energy interactions that happens at the boundaries of these control volume. Now identifying these interactions at the boundary results in the state space governing equation relating energy transfers relating the energy transfers and the changes in the cabin temperature. So the convective heat transfer coefficient, all the heat transfer modes along with the convective appropriate heat transfer coefficients are listed out and identified based on geometric orientation of the boundary surfaces. Conductive and convective losses are also evaluated based on the resistance network diagram. And I also have equations for AC and heater loads. So now the heat transferred through the roof and the windshield surface are governed by these control surface equations, which will be tied back to the control volume equations. Again, all energy interactions are identified at the control volume, at the control surface, along with appropriate heat transfer correlations. Okay, so here's the representation of my control volume simulating model. Basically, I have a heater control, I have an AC control, and I have my environmental parameters. Now I have the thermal band is set between thermal comfort limits is set between 23 and 27. The heater triggers on when the cabin temperature is lower than 23, and the air conditioning AC turns on and cabin goes above 27. Okay, so let's now look at how this model will be used to simulate a sample trip. So the slide here just represents a sample output from all the governing equations that were solved based on simulating. So let's consider a scenario where we decide to simulate an hypothetical electric vehicle and is exposed to ambient conditions at 29 Palms, California on first day of January. So here the plot represents the ambient temperature curves. Now the ambient temperatures can be seen to be varying from a minimum of 5 degrees Celsius to a maximum of 18 degrees Celsius. So during this period, since the electric vehicle is exposed to the incoming solar radiation, the maximum cabin temperatures reaches about 45 degrees Celsius during the hottest time of the day. So now let's say that we would want to start. We would want to go on a trip at 11 a.m. So as soon as a person enters the cabin, you would experience a hot cabin temperature of 35 degrees Celsius. Now, upon turning on the air conditioning system, the temperature is brought down from the soak condition of 35 degrees Celsius to 27 degrees Celsius, and the AC continues to maintain the temperature at 27 degrees Celsius for the rest of the trip. And it can also be seen, the trip is set to end at 1 p.m. and the temperature when the vehicle is turned off, the temperature further goes up and then decreases as the day progresses. So now looking at the power curves, just at the beginning of the trip, to pull down temperatures from the soak conditions, AC demands a peak power of 7.8 kilowatts for approximately 400 seconds. and an average of about 1.2 kilowatts for the rest of the trip to maintain the thermal comfort. So this roughly translates into about 0.52 kilowatt hours of transient electrical energy with 1.91 kilowatt hours of steady state energy, amounting to a total of 2.43 kilowatt hours for the entire 2-hour trip. So this scenario is representative of a case when cabin was not preconditioned at the beginning of the trip. While the blue curve here represents the case when the cabin is already at a set point temperature and the AC is only required to maintain the temperature from that point on. And so this would be representative of a case when of a preconditioned cabin. Okay, so just to recap, a single electric vehicle in a particular location was simulated on a specific day for a specific trip. Now, if I want to perform similar simulations in Detroit, obviously I would require that hour by hour temperature environmental parameters at Detroit in order to simulate similar performance. But fortunately, National Climatic Data Center distributes National Solar Resource Database, which is basically a database containing a set of all environmental parameters across 1,020 stations within US. And the trip times, to simulate daily trips, National Highway Transportation Survey database was parsed to obtain the trip start and end times of all the survey takers on the day of survey, and also the vehicle distribution was modeled from the US Census Bureau based on the demographics. So to put all this in perspective, I now have this vehicle thermal model, comfort model, which takes in climate data from an SRDB and it takes in driver behavior data from National Highway Transportation Survey, and it takes in UE geographical distribution data from US Census. And simulations are performed across 1019 NSRDB stations with 365 days a year and 24 hours per day, amounting to a total of approximately 18 million computations. So this, the output database generated from here would be used, would be further post-processed to answer specific questions, sub-questions related to each one of the research questions. Okay,
How long did the calculation take?
So the database itself was an Excel sheet, so reading all the data from Excel took a long time. But once it's converted into a native format in MATLAB, it was pretty fast using Celeris.
Hours?
So in terms of hours, every simulation for every location, it would be approximately 2 to 2.5 hours across all 365 days and 120 locations. Okay, so
to do 18 million
no,
simulations?
the 2 hours was for one location, one station. I didn't have a tab for 18 million simulations, but for every
Okay.
So it'd be 1019 times 3 hours or
times,
something like that. Yeah, CPU hours.
okay.
A lot.
Imagine that's
But I
still
did-
going right now.
But I did notice that with Excel, with just reading the data from Excel, it would take almost 2 days to just get the process started. Okay, so now let's go over some of the key findings associated with research question 1. So the first step towards answering research question 1 in its entirety requires that annual energy consumed by an individual vehicle be determined. So the graph presented here is a state-wise geographical distribution of annual HVAC energy consumed by a single electric vehicle. So clearly the variations are due to widely varying weather conditions. So the key takeaways is that Arizona requires approximately 1,000 kilowatt hours of electrical energy per year more towards operating HVAC compared to an EV user in West Virginia. So now what that implies is that for an EV user in Arizona, would be charging their electric vehicles about 54 times more frequently than an EV user in West Virginia. So from the user's perspective, due to higher rate of battery degradation, electric vehicle users in Arizona are at a disadvantage since they'll have to replace their batteries more frequently more sooner in comparison to those in West Virginia.
So West Virginia was the lowest use.
Right.
I wouldn't have guessed that. I don't know what I would have guessed, but I guess because it's moderate between heating and cooling. Yeah.
But in Colorado, we're so dominated by cooling, aren't we? That sunshine, yeah, we live a mile high. That sunshine gets into the car. Huh?
Okay, so from the EV manufacturer's perspective, it is also clear that they may install more charging stations in Arizona, knowing for the fact that the EV users are going to be charging more frequently there in that region. So the results here caters to the understanding of EV performance of both end users and automakers. Okay, so in the previous slide, we looked at the HVAC energy consumption by an individual vehicle. Now we look at the state-wise annual HVAC energy consumption for a 100% hypothetical light-duty vehicle fleet. So not very surprisingly, California leads this list with a list by 88% above US average. This is simply due to the fact that California has 14% of light-duty vehicle fleet concentrated. So now a 100% light-duty fleet may not be, may sound too unrealistic, it may not be feasible at all. But the research presented here allows us to perform simple calculations for HVAC energy consumption for near-term possible scenarios, be it at the state level or at the national level. So for example, in 2009, 60,000 EVs were estimated to be in the market, which constituted to be around 0.03% of the transportation fleet. So that amounted to about 0.14 billion kilowatt hours of DC. So now the utilities and the policymakers can use this kind of information concurrently with the EV sales forecasts to plan for the additional grid energy requirements as these numbers scale up. Okay, so in the literature discussions, one of the issues was regarding the previous studies and vehicle simulation softwares using a constant HVAC load in the vehicle simulation modeling. So the figures here present seasonal variations in HVAC loads for peak hour travel of 9 a.m. and 4 p.m. During spring, summer, fall, and winter. So clearly the HVAC peak hour load varies from 0.5 kilowatt to a maximum of 3 kilowatts during summer. And also comparing Nevada with Alaska, the maximum AC load during summer in Nevada is about 3 times higher than that compared to that in Alaska, but during winter, the heat load is 16 times lower. So ignoring these transients while designing the HVAC systems will result in propagating uncertainties greater than 150% with regards to thermal comfort loads. Okay, so in closure of research question 1, it is determined that about 415 billion kilowatt hours, DC kilowatt hours of electrical energy is required towards cooling, and about 151 billion DC kilowatt hours of energy is required towards heating for a 100% light-duty vehicle fleet. Now both AC and heat together accounts for about 35.8% of total fleet energy. And also electric vehicle consumes about 70% lower energy in comparison to a similar sized conventional vehicle. Also, electric vehicles results in 48% less carbon dioxide emissions in comparison to CVs. Now the key thing here is the CO2 emissions due to HVAC and EV includes both heating and cooling, which was never characterized before. And so that is about 36.5% of total CO2 emissions from electric vehicle. Okay, so moving on to research question 2. The objective here was to qualitatively investigate the geographical and temporal sensitivity of HVAC load. Now, in order to do that, a study of EV performances is constructed in 5 cities, and so the EV is chosen such that it is similar to an existing model in the market with a 24 kilowatt hour storage and a 0.3 DC kilowatt hour per mile discharge rate. So theoretically, under these conditions, one would expect to travel 80 miles, but we'll see that it is rarely the case. And so the 5 cities simulations were performed for 2 scenarios. First without preconditioning, followed by with cabin preconditioning.
Could you define preconditioning?
So cabin preconditioning is so when you have your electric vehicle parked and it is soaking under the solar radiation, the cabin temperature is going to be much higher. So now so if you have the ability to precondition the cabin before you start the trip, so say you turn your air conditioning system on before, there's a way of turning the air conditioning system on before you go into the vehicle, so you will enter a preconditioned cabin space.
And the benefit of that is that
So the benefit of that is in electric vehicles, it'll just let you travel much farther because the energy that is required. So when I discuss the sample simulation outputs, the energy towards cooling the compartment is spent towards transient, is spent in 2 ways: the transient and there is a steady state energy consumption. So if you precondition, you do not have to. Your energy storage device on the vehicle does not have to accommodate for the transient component. So it only has to accommodate for the steady state component. So that allows you to travel much farther distance. So that is so we'll see the benefits of cabin preconditioning in these sections. Okay, so US it has widely varying weather conditions. So the 5 cities that were chosen such that they capture these fluctuating trends. So the cities chosen were Anchorage, Atlanta, Detroit, Los Angeles, and Phoenix. So there's no surprises here. Mostly Alaska sees a lot of -20 to 0 degrees Celsius days. With Phoenix, you get more of 35 to 40 Celsius days. Now let's see how our electric vehicle performs in these 5 cities. Okay, so here's the results from 5 city simulation for day-to-day and hour-to-hour variations in EV range. So
Can you go back just a second? So, LA is Los Angeles,
yeah.
and it's not, I'm surprised it doesn't have significant cooling.
No, this is the day-to-day ambient temperatures.
Okay. Oh, okay.
So this is just day-to-day ambient temperatures, local average ambient temperatures.
Let's say there's no heat island effect or something.
And the smog, actually, there's a benefit of smog.
do you know? I mean, LA is like 100 miles wide. Do you know what the location of the NSRD site was?
Gotta be
Yeah,
in
that's
Orange,
true. Yeah,
gotta be in an orange
Riverside.
grove somewhere, you know?
Yeah, well, I mean, if it's on the
Yeah,
ocean,
It would have a lot of.
There's no variation.
Malibu is pretty nice.
Yeah.
Riverside sucks.
But you can see, I mean, it gets down to 10 Cs, 5 days a year.
Yeah, just that there's almost no red in it. That does
Yeah.
initially surprise me.
There's almost no variation in it.
Yeah, there's a few stripes of red, but.
There's more red in Detroit than in LA.
Right. Well, it's just very
But-
uniform.
Yeah.
It's almost all Saturdays that it is.
72 degrees and sunny every
Cut it
day.
all out.
Right, so let's look at the EV performance in all these 5 cities. I have day-to-day and hour-to-hour variations in EV range in Anchorage, Atlanta, Detroit, LA, and Phoenix. So for Anchorage, it is about 64.2 miles, while in Phoenix, it is lowest at 60 miles. So from these plots, let's say I want to determine what the expected EV ranges for my trip tomorrow at 8 a.m. for my office. It's about, so I would be getting 65.7 miles in Phoenix to about 77.2 miles in Detroit. Now, performing similar simulations with preconditioned cabin, in this scenario, I can see a maximum of about 8.3% increase in EV range in Phoenix with very small percentage increments in other cities. Okay, so
For December And this is for December 6th.
December 13th.
So isn't it cold in Anchorage? And so why can I really drive as far in Anchorage as, am I not using any heat in Anchorage compared to Detroit or LA?
It's possible that the soak conditions are just enough, just within the comfort limits that I've set. in
What's the
model.
temperature in
So-
Anchorage on December 6th? It's cold, right?
But it's preconditioned.
I know, but you're so you're only using the running losses, but I have a hard time believing that the running losses that there's no heat in Anchorage,
So
and that it's the same as
0 C ish.
so, okay.
So you can read off like 0C at, you know,
50, yeah, so 0 C. Well, yeah, everything everything from the last 2 months is 0.
yeah.
Okay, all right. So let's go to now. Go
So
to
then,
all right. So
so go to the previous slide, Ron, one more back. So here, you can see that in Anchorage, it does take, there is some energy taken there. It's on the order of, you know, it's between 75 and 80 miles is your peak range. Or is your range of the
range.
okay, so
this is
I
for-
believe Phoenix is air conditioning. We pretty much know that LA is probably not. So I guess it cost us a little bit.
So, but I mean, you're right. I mean, there's energy used. It's
Yeah.
just,
Okay.
it's
It's not
It's a surprise to
significantly
me.
affected. Okay, so now in this slide we will look at the results that would help us understand the relation between trip start times and the benefits of cabin preconditioning. Again, at all the 5 cities. So I have electric vehicle range on my y-axis and trip time on the x-axis. Clearly, EV range drops off during the hardest time of the day, and it is easy to notice that the trip time does play a role in determining how beneficial the cabin preconditioning is. So for example, if I were to pick Phoenix, for a 6 a.m. trip, I see a 3.7% increase in EV range, while it is about 3 times more for a 11 a.m. trip, approximately at 10%. Okay, so now let's look at how an EV manufacturer's claims of a particular EV range tally with our simulations. So as an EV user, I'm more concerned, I'll be more interested in wanting to know how frequently I can travel the range specified by the EV manufacturer throughout the year. And so to test this, let's consider Phoenix, Arizona as our sample test location. And I have these histogram plots here, which basically represents the frequency in terms of number of days of year one can expect a certain EV range for trips starting as a function of time of day. So for example, for a 12 a.m. trip, I can obtain an EV range of 65 miles for approximately 21 days of the year. So now with this help of the histogram plots, it's easy to test the claims of EV manufacturers. So let's say, let's consider Nissan Leaf, which is again 24 kilowatt hours. So their EPA averaged drive range is 73 miles, while the Nissan's reported range is 75 miles. But it can be seen that one gets 73 miles or more for 8 a.m. trips only on 31 days without cabin preconditioning, while 31 days of the year without cabin preconditioning, while with preconditioning it goes slightly higher to 52 days of the year.
For only 31 and 52 days.
Right. So this here's my 73 miles is the EPA weighted average range claimed by Nissan. So now from for a 8 a.m. trip, if I look at how many days of the year I can get 73 miles, it will be the sum of all these number of days, and so that is only 31 days of the year. It's
Without.
right. And so it is 52 days with cabin preconditioning. So it's not really 365 days as claimed by EV manufacturer. Okay, so now for an automaker, it is important to identify the regions within US where EVs can lead to greater user satisfaction and subsequent greater EV sales. So the greater user satisfaction may be experienced when the day-to-day variations in EV range diminishes. So this figure here represents state-wise maximum, minimum, and mean EV range for a particular driving condition. So the length of the bar between the minimum and the maximum range is indicative of the fluctuation in EV range within a state. And the smaller this fluctuation or smaller this difference, lower is the sensitivity of EV range to weather. So the plot on the right shows the magnitude of this sensitivity in terms of range differences between minimum and maximum. So it is seen that the conditions in Delaware is most favorable for EV operation with very minimal fluctuations. So this gives a good starting point for establishing EV sales strategy based on performance data. Okay, so closure of research question 2. We looked at the geographical and temporal sensitivity of HVAC loads on EV range, and are there regions of country that are most advantageous or that should be precluded from vehicle fleet electrification? We did see that the answer to that is yes. There are regions where EV range is less sensitive to weather and hence possibly could enhance user experience. Now, we also did look at the EV performance as a function of time of day. The EV performance drops during the hottest time of the day, and it follows an inverted bell curve with lowest range during hottest and coldest time of day. And so cabin preconditioning was also determined to assist in improving the EV performance by about a maximum of 12.5%, and that depends on the trip times of the vehicle. Okay, so going into research question 3, again, the objective here was to look at technologies that would decouple the HVAC requirements from the main onboard energy storage device. And the objective of ARPA-E HEATS program is to identify and support the development of alternative HVAC technologies. Now, the technologies under consideration, as defined by ARPA-E, should also meet the vehicle HVAC requirements without draining the main vehicle battery, and it should also not have any additional increment in curb weight of the vehicle. So with this, we looked at a phase change material based HVAC system, such as a combination of ice water and for cooling and paraffin wax system for providing heat to evaluate the requirements of PCM mass based on day-to-day HVAC requirements. So in this discussions, we'll also look at a multi-objective comparison of the state-of-the-art vapor compression refrigeration systems, vapor compression AC system in the electric vehicles with the PCM-based system that we'll discuss now, along with the ARPA-E heat scope. Okay, so here again I choose the same 5 cities for comparison purposes. The figure here represents the paraffin wax mass requirements based on the day-to-day peak heating requirements in these cities. So it can be seen that the PCM requirement in Anchorage requires a maximum of 42 kilograms of paraffin wax, while it's only 18 kilograms for a location like Phoenix. So now a system designed based on the needs of Anchorage is going to be twice oversized for the requirements of Phoenix based on these peak thermal comfort requirements. So now again, performing similar analysis using ice water based PCM system. Mass of the PCM is in Phoenix is close to 65 kilograms, while that in Anchorage is close to 43 kilograms. So in summary, the combination of the total PCM mass itself is not very different, but the relative difference between the individual system varies from a maximum of 46 kilograms in Phoenix to a minimum of 7 kilograms in Anchorage. So this variability in requirements have to be accounted for in designing the alternative accessory technologies and its subsystems. Okay, now we'll look at the multi-objective comparison of conventional vapor compression-based HVAC system with the resistive heater, which is as used in the present day EVs, without and with the ability to precondition the cabin while attached to grid before driving, alongside the PCM-based system and ARPA-E heat score.
So curious, why resistive heating instead of heat pump for the air conditioning? Well, why not heat pump heating?
So I think
Because you already have it there with the air conditioning, right?
right. I thought resistive heaters were used predominantly in electric vehicles to provide heating.
I don't know.
In addition to heat pumps. Okay.
There could be, but wouldn't we get? I assume that the coefficient of performance for a heat pump would be significantly better.
Right. Yeah, I was under.
Like 4 times better, you know?
Yeah.
Okay.
I don't know how it's actually done, but I'm surprised they wouldn't be using that. But
So right now, and we started this research in 2010 or something like that, and the Nissan Leaf up until I think it's 2014 model year has been a vapor compression air conditioner and a resistive heater. And so actually this year, I think it's 2014 model year, right? They're
Changing
moving
over.
to heat pumps.
Oh, okay.
Yeah.
Okay.
And it's all about, I mean,
What-
it's I think the real reason that they're doing that is that it's they're basically they're planning and doing a nationwide rollout of the vehicle. So rather than putting these vehicles in California and Phoenix or California and
Oh, okay,
Arizona
okay,
and
okay.
Florida
Okay.
and New York City,
Right, you weren't
they're
putting
also
them in-
going to sell them in Chicago.
Okay. Right.
Okay, so here I have, so this figure here, it represents AC energy consumption in watt-hour per mile, evaluated for the minimum and maximum range days, basically US days, across the suite of technologies that just described in the previous slide. So I also have the modeled vehicle mass and also the corresponding EV range. So it can be seen that these advanced technologies, they do not necessarily do any good in terms of the energy consumption itself and hence the greenhouse gas emissions, but they definitely reduce the sensitivity of, they definitely increase the electric vehicle range and improve the perception of EV users and just makes them more reliable. So now, looking at the percentage of people who would travel 80 miles on a daily basis, from the NHTS, it's only 2%. So it might seem like we are investing in technologies to cater to the requirements of these 2% of, just these 2% of people. But the important point here again is that it does add towards lowering the perception of range anxiety. And so in closure, cabin preconditioning, PCM thermal storage and advanced technologies will definitely improve the performance of electric vehicles, and all the on the downside, all these advanced technologies will certainly require preconditioning for leveraging maximum benefits, and they do not do any good in terms of improving the energetic and GHG emissions. But the advanced HVAC technologies definitely reduce the range variability rather than quantitative utility.
Okay, so the second point, energetic and GHG benefits are not in evidence. There are benefits.
There are benefits in terms of increasing the EV range, but then there has to be, the energy has got to come from somewhere in order to use the technology.
So that's weird, right? It's sort of like it's not actually, the technology is trying to make benefits through the pathway of improving consumer acceptability, right?
Right. So it's like
it's making EV, it's saying,
Yeah, right.
If we can
Power
make-
for cooling is coming from somewhere.
right.
yeah, so it's sort of saying maybe we can get benefits out of an advanced PCM system but it's going to come by making these vehicles more acceptable to the consumer, not by actually saving energy, which is kind of interesting.
Okay,
Even with the round trip, I mean, and this accounts for the round trip efficiency of storing in the battery and then, right? It accounts for battery costs, right?
I mean, you could see, like, if you go back 2 slides, should have that slide again. Yeah, you know, there is a slight, non-dominated difference, improvement with these technologies, but it's dominated by variation in the way you drive the vehicle.
I still have a question about preconditioning. So, where we flash forward 10 years, the engineering parking lot is full of electric vehicles. They're all being maintained at interior conditions of 72.
Is that a good idea?
That facilities looks at the kilowatt profile, and Carol Dollar goes, "Holy, what is going on here?" And then we say, "Well, we're saving energy by preconditioning." And meanwhile, you've got all these cars doing nothing more
Put
than
in a
just...
separate meter.
Yeah. So who pays the bill for preconditioning?
Well, if you're at
No.
a charge station that you pay for, you do.
Yeah, right.
But it's also, in a lot of this, they look into, your average trip. You're going to work at 8 a.m. and going home at 4. You set up your preconditioning turn on an hour before each of those trips, and then you don't have it running the whole day. You only have it running
But the
at a
energy,
slow ramp. It's still the energy to get the heat there, right? But you don't have the spikes and the power to require to provide the heat or cooling or whatever.
So how long does it take to cool? I mean, you normally get in your car, it takes 5 minutes to cool down. Is that right? So maybe that's.
Thinking your 29
But-
pounds example is 400
400
seconds.
seconds.
To cool down the vehicle.
Of course, that's not. It's the air cool. It's not. You've still got a lot of hot mass. So, and I suspect that's. I don't know what's reflected in that transient cooling. Is it just to cool the air, or is it to cool the rest of the mass in the interior of the vehicle?
So the way I have this model set up is the single point representation of the cabin space temperature. So it would be more of bringing the temperature of the cabin air to the comfort limits.
So, but the point is that this is what utilities fear, is that we're going to be air conditioning your work when you're not at work, and your house when you're not at home, and your car when you're not in your car. That would be really, that'd be bad news. So, but in this model, do you recall what the amount of, how much energy we used to do that preconditioning calculation for the energy, for the AC energy
Yeah,
use?
relative to that transient.
Yeah.
In the initial transfer.
No, so
Okay.
go back
You
one
had the-
slide, Karan, and then so in that AC energy consumption, that includes the energy for preconditioning. Do you recall what? I think it was, we did 1 or 2x, so as if you had started at 5 minutes earlier than you would have.
It was like
So it's-
8
it's a little bit-
kilowatts for a small amount of time, or something.
Yeah.
I just want to remember.
Yeah, exactly.
Okay.
So the economics depends on the relative difference between power and the cost of power and energy. Then. I mean, you could probably do that calculation. In terms of what kind of demand charge you have to pay. What your cost per kilowatt versus the cost per kilowatt hour.
Right.
The idea is that you're moving that off vehicle for the requirement as
Yeah.
opposed to having it.
Yeah.
So with the demand charge for Ford Collins is 20 cents a kilowatt.
Depends if it's if you're.
No, it's not.
It depends
coincident peak-
which residential are you general service? A general service 25. I don't know off the top of my
Wrong
head.
answer.
I don't know off the top of my head.
Well, isn't it something like $18 a kilowatt?
If you hit both of them, the peak and the coincident peaks, it's like 18.
$20.
And we don't have residents that does not have.
Yeah, so it's, what's $20 times 5 kilowatts, or 8 kilowatts times 500 cars in the parking lot? That's all. That's the incremental utility bill. It's a big lot.
Yeah.
But you're gonna have time of use pricing on your your meter, so
Mhm.
there's a,
So you'll pay for it somehow.
Okay, so looking at some highlights of some of the contributions, major contributions, we made an attempt here to evaluate the metrics from each of the stakeholders' perspective. So in this context, a new state space approach towards modeling thermal comfort was adopted, moving away from the traditional fan jet approach. Now, with the integration of NSRDB, NHTS, and fleet distribution all within one model, it is now possible to obtain more realistic estimations of vehicle and fleet level energy consumptions. In addition to that, a variety of sub-studies were associated with EV performances were performed. It is now possible to achieve a very high resolution of EV range as a function of geography, if required both at the city and also at the county levels. They are only limited by the accuracy of the weather data, and the study can also be extended to other parts of the world. And a qualitative assessment of advanced auxiliary technologies were presented, and this should enable the automakers to judiciously incorporate region-centric designs and provide innovative modular packages for cooling and heating that can be scalable. Okay, so traditionally the question of providing thermal comfort was highly localized to subsystem design. Now, NREL took these models, incorporated them into naive models of operating environment. This approach was good for generating first order estimations, but it would obviously result in discrepancies towards evaluating supersystem metrics like greenhouse gas emissions. Now, through the stochastic simulation integration of operating environment with advanced with system design and the vehicle design, it is now possible to move closer towards estimating real-world supersystem metrics. So with this, I conclude my presentation, and thank you everybody for your kind attention.
So I know this is kind of like a worst case analysis, but does NHTS include information on how many people have garages? Because you're already preconditioning.
Yeah, I was at the same thing.
Not in this study.
And I would imagine that a lot of people that are driving EVs probably have garages that they're parking them in, so it changes that incremental difference than, or maybe a conventional vehicle you don't consider parking in the garage as much as you would your EV because you have to charge it when it's in there or something like that.
and if you're in rail or RMI, you're also parking into the carport.
Right.
So you're parking in the shade.
Yeah, so I mean,
a tree is also a
HVAC technology.
So it kind of helps, right? Because then it's only going to likely be in a garage when you're leaving from home. During your daily trips, it's going to be outside. That's when the lower loads are during the day. So
Right, absolutely. So what I've shown here is some sort of cabin preconditioning is going to help in improving the electric vehicle range. So we looked at those curves where the cabin preconditioning had a major effect depending on the trip starting times, right? So in terms of looking at the EV technology itself, it definitely requires a different perspective to look at the EV technology as against conventional vehicles. So parking. So if a person buying an electric vehicle would naturally start to think that to maximize the benefits of that, having a garage would be most beneficial. But I guess, for this model, I've not looked at those factors. I've more looked at the trip start time itself.
So Fahringer has his 4 parameters,
Right.
and which of those you are only changing temperature, right?
I'm having solar irradiation, and I'm having hour by hour average ambient temperature.
Right, but I couldn't I have also gotten to my reduced my dissatisfaction by increasing air velocity, a fan, or dehumidifying, or I guess radiation.
Right, radiation.
The argument there is very subjective from person to person. And so what I would consider as thermal satisfaction need not be a thermally controlled environment for another person. So there's all these fighting.
Well, okay, so the other thing on thermal comfort is also, it also changes from, I mean, it's very different. Yeah, India, Asia, Africa, Europe, and US all have very different set comfort set points on what people are comfortable with. I'm just, is the satisfaction index the same in Texas as Alaska?
I would guess definitely not.
What if that's
Yeah, I mean, in Phoenix, you got the flip-flop thermal comfort. Texas, you got the cowboy boot thermal comfort. And then you got the Sorrel thermal comfort.
No, even within Texas, there could be.
Just one small. It's the same as buildings.
Yeah.
So it's like we got in Denmark or whatever, I mean, it's applied everywhere.
Yeah, and so if it's in Denmark, it's people that are just fundamentally best satisfied. Or in Texas.
I would have had it, actually.
That's why it goes to 80%. You don't care about it. Because you know in Denmark, you never get any better than 80%. You know?
We could use this strategy and you just cut the heating load by having 10 people in the car. What we're doing here.
No, but that is actually, you have two options, right? If in a vehicle, if you want to reduce the temperature of the air that's baked up, you can cool all that air, or you do what you normally do is you blow it out. But, I mean, there's a good tool here. I'm just wondering if you've given thought to the to whether cooling, direct air cooling is actually the best solution to improving thermal comfort.
I don't think I've necessarily looked into that aspect of it, but
Any conjectures?
so just from reading all these literatures and opposition to fan blades, I was convinced that, and also there has not been any, and also so the fan blades approach was more developed towards building applications, and so now we have this confined cabin space that is more sensitive to the fluctuations at the boundary of the cabin itself. The control volume is much more smaller compared to a bigger building. So I would be so I was tempted more to represent it. Why are people not representing this based on energy interactions itself?
So what's the really? I suspect there's a bigger difference between vehicle comfort and building comfort, and that's the direct conduction to the seat.
Right.
A lot more sunlight too.
And that's why you have seat heaters, and BMWs have seat coolers, but I'm not sure why else does.
Oh, Subaru has excellent seats.
I mean, I think it's a good question. So, for instance, how does NREL or the Fander model or anything else like that? Like, let's say the big differences in vehicles are could be the conduction to the seat and this sort of stuff, and solar irradiation, right? I mean, that's a big thing that is in the vehicle that's not in a building or whatever, right? So, for instance, how does Fander's model or NREL handle solar irradiation?
So the way they handle the solar radiation is by accommodating what is called as a mean radiant temperature. So in one of the so the way they accommodate that is, because of this thermal soak, there's going to be an increase in the delta T. So they come up with this operating temperature, which is basically an average of the local ambient temperature at that point of time, and a mean radiant temperature up to that point of time. It's basically like a cumulative temperature, and so they use that temperature to determine what the thermal comfort
And
is.
it's cumulative over what kind of a time period?
So it's cumulative over. I guess they are using it from say 12 noon to 3 p.m. over a period of 3 hours to predict the worst case scenarios. But
So,
in-
I'm sorry. Go ahead.
yeah, but in my model, I actually have it resolved hour by hour. I have solar irradiation and the ambient temperature coming in hour by hour. So I'm not accounting for by means of accumulating energy and things like that. So it's basically a state space representation of the cabin temperature, that particular point of time affected by the solar irradiation and the whatever the ambient temperature is going to look like in that location.
So the advantage of that is that it lets you, I mean, I guess it lets you look at the temporal variation.
Yeah, it's
I mean,
right.
rather
It's
than
much
being-
more accurate representation of what of your EV drive range.
Any other questions?
Yeah, there was. I think you mentioned like you get a shorter range most days of the year because of the HVAC than what they were predicting. Like they're predicting like 77 miles or something like that, and you only get that 51 days. I'm guessing that's pretty standard though for like a conventional vehicle when you get like the miles per gallon or any, or if you have a range on that, they're not worrying about HVAC at all on that, are they? You know.
Probably be different if you only had a, I don't know, what's the battery equivalent of fuel? So if you got
1 gallon.
it's 40 kilowatt hours per gallon, right?
Yeah, it's 1.5
Okay.
gallon.
Yeah. If you had a pint of fuel, you'd be more concerned.
It's much more discernible in the summertime because in the wintertime your heat's going to come directly off of your engine.
Yeah,
I
that's
don't
it.
see that as actually a fuel loss for the most part.
Exactly.
It's air conditioning based.
So what would be in the same, go ahead, Alan.
Well, no, I just came up with some ideas, but this is after people leave.
Okay.
Yeah.
So then what would be, what are there implications, are the implications of this like specific, you think, to like a low range vehicle? Or is it something like if you were talking about a Tesla that has 300 miles of range, which is, you know, the functional equivalent of a conventional, maybe not a, you know, a little Honda, but it's a conventional Chevy Malibu-ish thing or something like that, then is that, are the implications the same? I mean, do we have to care about HVAC range even in a Tesla?
Right, we definitely have to care about HVAC. Just by increasing the size of the battery, this problem is not going to go away. So the more, so a person buying a Tesla with 300-mile range would plan to use their vehicle accordingly. So they're going to train themselves to use their vehicle to make the most of those 300 miles. It may not be within the same time frame, but definitely they are going to see the fluctuations in HVAC requirements, and they would still feel dissatisfied as a person with 24 kilowatt hour battery. So the problem is inherent in the technology itself. It's not going to disappear. The fluctuations are not going to disappear as such. So the solution is not really increasing the capacity or the size of the battery itself, but it seems like that's the apparent solution for the automaker. Like Nissan started seeing problems in their Leaf in Phoenix during summer, and very recently they just increased the warranty of the batteries from, I guess, from 6 years to 8 years. And so they're doing all these measures, but if you look at it, all these are towards making the EV users experience better and better. But so it comes down to the EV users themselves on understanding these variations, so that it would do them more good in terms of getting more benefits out of their vehicles.
Okay. So you think you could offer the automakers to sell their electric vehicles from the factory with tinted windows? That would help them extend their range?
They do.
So they already know.
We're a free
They
code.
tend to do the national limit.
Okay, so they already kind of know this, what we just learned here today.
Just where are they willing to invest their money in technologies?
Absolutely, that's what I meant by region-centric designs. So if you know you're going to sell a vehicle in Alaska, the design has to be tweaked according to the requirements there against a vehicle sold in Atlanta or Phoenix. So I guess it's time that they look at it from this perspective than just scaling up the heating or air conditioning system over the entire fleet.
Okay, well, let's just give Karan one more round of applause. Thank you all for attending. So if we could dismiss the general public and keep the lead, that'd be great.
Freeloaders.
Yeah.